2.7, we're talking about bond enthalpies. So during a chemical reaction, bonds are broken and formed, and these events change the potential energy of the system. The average energy required to break all of the bonds in the reactant molecules can be estimated using average bond energies. So these energies associated with various types of bonds have been calculated based on the decomposition of the compounds that contain them. These are often called bond dissociation energies, which is the amount of energy needed to break the bond between two atoms. So when you have data, it's talking about two atoms only and the energy associated with breaking that bond between those two atoms. So when they're tabulated, whenever you look at a table, these energies are averages based on experimental data. So if you get a case-by-case basis, they might slightly differ. So this table is on page 4 in your notes, but notice that bond energies will increase as the number of shared electron pairs increases. So that means the number of bonds between them increases. So just to point out how that works, a carbon-carbon single bond has an average bond energy of 347 kilojoules per mole. But then if you look at a carbon-carbon double bond, it's 614 kilojoules per mole. And a triple bond is 839. So they do increase, but they don't double or triple. So you just have to be careful there. But just know that the more electrons being shared, the more bonds between them, the stronger they will be. So the more energy is needed to break that bond. And so again, these energies are how much energy needs to be put in to break the bond holding these two atoms together. When we have number of shared electrons increasing, so more bonds between two atoms, the actual length of the bond will shorten. And so that's seen here in table 8.5. You can see that as the number of bonds increases, the length will decrease. Well, what happens to the bond energies? We kind of saw this before, but as the bond energies will actually increase as you increase the number of bonds between them, or as the number of shared electrons, and that's because they're just getting stronger and stronger. So noting that correlation is important. Bond energy values can be used to calculate approximate energies for reactions, where the capital sigma, that's that E-looking thing, represents the sum of terms. D represents the bond energy per mole of bonds, which that would be found in the table. So you get D from the table, 8.4. And D is always positive. We just always plug it in as positive. And then N represents the moles of a particular type of bond. So N is the number of that bond. So it's important to notice here, and this is backwards for most things that we have, that the bonds broken represent the reactants, and the bonds formed represent the products. So essentially, yes, this is a crazy little equation, but essentially what we're going to be doing is we're to find the enthalpy value, then we will take the reactants minus the products, making sure we multiply by the number of bonds there are and using the correct numbers from the table, but that's essentially what we're going to do, okay? In 8.5, we actually switch around, but for now, it's reactants minus products for these bond energy values. So now, if we know that the energy released is greater than the energy required, the reaction is exothermic. If the energy required is greater, then it's endothermic. What does that mean? In different terms, it's still saying the same thing. That the energy released is talking about the products, and then the energy required is talking about the reactants. So if the product's energy is greater than the reactant's energy, that will become a negative value, which would mean exothermic. If the flip side happens, where the products are smaller than the reactants, then it will be endothermic. So again, The exothermic will be shown by having a negative value at the end, and the endothermic will be a positive value. So this still follows everything else we've been talking about this unit, but it's just knowing that energy released talks about the products and energy required talks about the reactants. So let's try example 9 just so that we can see where these come from. Now, all of the energies that I'm going to be using are listed in table 8.4, which can be found on page 4 of your notes, or it's page 374 in the book. So if you, for some reason, don't have your notes with you, page 374 in the book also has table 8.4 for you, okay? Now, so we have this reaction. We want to figure out the change in enthalpy for the reaction of methane with chlorine and fluorine to give Freon 12. And so we have this big old equation. Now, remember in the equation where we had to take n times the energy? Well, that means that we have to know how many bonds are actually present before we multiply by that. So it might be helpful to think about the Lewis structures to know how many bonds. So for CH4, that's just going to be a carbon with 4 hydrogens around that. So that means that we actually have 4 CH bonds. Okay? Then for the Cl2, the Cl2 stands for ClCl, but if there's a 2 in front of it, that means that there's 2 of those Cl single bonded Cl molecules. Okay? So we're going to have to take 2 times the Cl single bond value. Then the same thing with the F2, the fluorine gas. That little 2 right here stands for the FF, but since we have a big 2 in front of it, we have to have 2 of those, so we're going to take 2 times that FF value. Okay? Then for the Freon, which is the CF2Cl2, the carbon is the central atom there because carbons have 4 valence electrons, and so 2 of the valence electrons are paired up with fluorines and 2 are paired up with chlorines. So in this molecule, we have 2 carbon-fluorine bonds and we have 2 carbon-chlorine bonds. So that means that we have to look for 2 different values for that Freon 12 compound. And then for HF, the HF bond, there's just 1 of those, but there's the 2 in front, so that means we have to double that value. So that's going to be 2 times the HF value. And then for the HCl, same thing as the HF, where we have HCl is the actual compound, but then there's the 2 in front, so we have double of those. So we need to take 2 times the value from the table for the HCl bond. Okay, so I'm just trying to show you why I'm multiplying by the current numbers that I'm going to multiply by. Okay, and we always, when we do it, remember that it is reactants minus products. So what I'm going to do is I'm going to just find the total reactant value and find the total product value before I subtract at the end. Okay, so these numbers I found in the table on page 4, table 8.4. If you look up the CH bond, that is 413. So we have 4 times 413 for that one. And then that's going to be added to 2 times the chlorine-chlorine bond, which is 239. Okay? And then 2 times the F bond, and that is 154. Then for the, now here we have 2 numbers, remember. So we have 2 times the CF bond, which is 485, plus 2 times the CCl bond, which is 339, plus 2 times the HF bond, which is 565, plus 2 times the 427 for the HCl bond. So now like what I did before I actually wrote this out, because I felt like I had a little bit more space on my paper, is all of these numbers that I got from the table, I wrote them next to the bond so that I knew where they came from. If you're having trouble distinguishing that, come and look at my copy of the notes and see what I did, and maybe it'll help you out, or ask me about it. Okay? But so now, for simplifying a little bit before I add together, I got that to be 1652, got that to be 478, and 308. So the reactants are 2438 kilojoules. Okay, and for the products, I 970 simplified and 678 plus 1130 plus 854. So the products are 3632 kilojoules. Okay, we're not done yet. So now we have to take the reactants minus the products to get our actual delta H. And I need to clear my screen because I don't have any more space. So for delta H, which is reactants minus products, I will take 2438 minus 3632, and that gives negative 1194 kilojoules. So that means that that is the amount of energy. Now, since it's negative, that means it's exothermic, so that's the amount of energy released per mole of the freon, which is the CF2Cl2 formed. Okay, now for rounding for significant figures, since we are adding and subtracting, in this problem, yes, we're also multiplying, but in the end, we are going to subtract, so you just keep number of decimals, which is a whole number, and so that's why it's not rounded any further than that. Okay, so these are what you're going to practice with the homework problems, and please ask me questions if you need help.